resistance. Think of it like electrical friction. It's resistance to the flow of charge. And this is where we start to talk about, we'll start to talk about ohmic and non-ohmic materials. And we'll start to talk about Ohm's law. So R equals delta V over I. Resistance is equal to the voltage divided by the current. Twinkle, twinkle, little star. How does this go? Dad for that one. But it's another way to remember this equation for resistance, voltage, and current. Yeah. Ohms are the measurement that we use to measure resistance, and it's given with the Greek letter omega. You'll get good at drawing these. And 1 ohm is 1 volt divided by an amp. So it is a derived unit. 1 volt divided by 1 amp. And this is where we talk a little bit about the fact that all materials have characteristic resistance. You know intuitively, because of experimentation, what kinds of things are good conductors and what kinds of things aren't. Things that transmit current and typically heat well are conductors. Things that tend to not transmit current well are insulators. And it's generally a constant for any given material. So for copper wire, for a piece of ceramic, for air, for a piece of plastic or wood or any other metal. Who knows what metals are? What metal is the best conductor? You're probably going to know this because you've built computer components. Yeah?
Yeah, there are some like, I know there's.
Okay, so length, the farther in the pipe, farther in the wire, current has to flow, the higher the resistance. Cross-sectional area affects resistance, and so does temperature. So, when we get, I don't know if we'll get the liquid nitrogen while you guys are still here or not. There are transformers. So one of the big issues with moving current long distances is resistance over long distances of wire. So you can do a couple things. You can really jack up the voltage so that you can move the current as far as you want and not have too much loss due to resistance. That electricity moving through the wires heats them up. And that, of course, increases resistance. So you've got a double problem. There are places where they do chambers like this that are filled with this super cold liquid. Guess what? Liquid nitrogen. And cooling the wire down to a very, very low temperature decreases resistance. So when we go get the liquid nitrogen, there's a very quick little, so cute, experiment we can do with a very thin piece of wire dipped into liquid nitrogen. And it's so thin and it's so long that it doesn't transmit current to even an LED. Dip it in liquid nitrogen, the LED will light up because you're decreasing the temperature, so you're decreasing the resistance. And these are the problems we did yesterday, and the practice problems on 703 were assigned, and they're up on the board, I think. Yes, 1, 3, and 5. So now we're going to just get into, and we're going to go into circuits, and we have to learn how to calculate multiple types of resistance for circuits. So there is a tutorial online that I'm going to link to Classroom that's going to be an intro to circuits, but we're going to actually walk through it because we have the time now. Here's the big thing for a circuit. You have to have a source of potential difference. So remember we said that potential difference, voltage, if we think about it in terms of a battery with 2 cells, we have 2 terminals. Basically we're piling up electrons on one side. It's like pushing a bunch of rocks up a hill so that we create potential energy for those rocks to fall. We're piling up electrons on one side, and then when we connect those terminals, the electrons can flow into the other side until there's no more potential difference. That's when the battery's dead. The other thing that any circuit has to have is an unbroken pathway. And we utilize this to actually turn circuits on and off at will. Okay, simple circuit. Power source. And some piece of wire. That's a circuit. It's a complete circuit. Now, we typically don't see circuits like that. We typically see circuits that have some sort of resistor in them, or this is kind of silly, you're just moving power to move power. Why? More often we see it with some device in it. So here's a circuit with a simple light bulb. Now, to make to turn off this light bulb, what would we have to do? Okay, so this is a 6-volt source. As the circuit is drawn here, we'd have to disconnect the battery, which we can do. I mean, that's not hard. But what's easier is if we put a switch in. And switches typically look something like that. So now we have a switch that we can open and close. When the switch is open, the circuit's broken. We're not transmitting current to the bulb. When the switch is open, when the switch is closed, we have a completed circuit. Okay, here's what I'm going to do. Okay, equivalent resistance in the circuit. Because these are all in series, R equivalent, which we write that way, is equal to R1 plus R2 plus R3. Huh? EQ, equivalent resistance. So this is easy. It's equal to 5 ohms plus 3 ohms plus 1 ohm. It's equal to 9 ohms. Easy peasy. Cool. 9 ohms. Okay. What if we have... Okay, so we've got this circuit. We've got two in parallel. They're both 5 ohms. To solve for this, we do 1 over equivalent resistance equals 1 over R1 plus 1 over R2. We get an equivalent resistance, we get a reciprocal equivalent resistance of 2 over 5. So equivalent resistance equals 2.5. We've actually cut the resistance of the circuit in half. If we had just put in one of these by itself, we would have 5 ohms of resistance. By giving the current 2 paths to flow through, we've cut it in half. These are the kind of problems that are really easy to, well, not really easy. They're convenient when you have a given set of resistors and you have a need for a very specific current. This is where you start looking to make combinations that will get your resistance to where you want. Yes, ma'am? R equivalent equals 2.5. Okay? Really, really easy as long as you are only dealing with circuits in series and in parallel. So, of course, I'm going to give you a few of those, and then we're going to scramble it all up. Okay, so assigned, page 739, 20, this is section 20A, 1, 2, 5, and 6. Okay? These are all just in series. These are ridiculously easy. Not a problem. Also assigned, so let's... okay, so we've got 20A, which is series, 20B, which is parallel, 2, 3, 4. Page 739, page 744, and I'll give you time to work. Tomorrow we're going to work and look at these. Yeah, tomorrow you're just going to work on the problems and we'll chit-chat, and we may introduce complex circuits tomorrow. We'll see where we get to.